Japanese. Oh, okay. I was gonna say. I did not know you speak Korean. Hey, did you born in Korea?
Yeah.
That's cool.
2 years ago.
Oh, that recent.
Okay. Shall we?
We shall.
Accumulation functions. So remember before when we did fundamental theorem of calculus?
Yeah. You didn't even notice.
No, you didn't. I was trying to run him over. Okay, when we did a fundamental theorem of calculus and we said, oh, the area under the curve equals the total change in f of b minus f of a. Yes? Yes? Are you with me?
Yes.
Okay, so if you integrate, if you have water in a tank at a rate of root t plus 1 gallons per minute, and then you want to find out how many gallons have been pumped into the tank in the first 5 minutes, then all you do is integrate from 0 to 5, right?
Yes.
Yep.
Okay, and then if you're traveling with velocity of this and you want to know the total, let's say displacement.
Wouldn't it be a traveled?
In 3 hours it travels, or traveled, sure. Well, no, it is traveling, so it's currently traveling. In 3 hours is just the integral from 0 to 3 of the velocity function, right?
Yep.
Yes.
Okay, now you can rewrite the integral from a to b of f of x dx in this way. You can solve for a specific location on the original function if you move this f of a over to this side, right? And then I can solve for any point on x. I don't find total change anymore. I actually solve for one location on the original function, right? That's what's called the accumulation function. So you can find any point on the original graph if you take the location that you have, like this is basically your initial condition, what they give you to start with, and then you add your total change from your initial condition, right? Then that will tell you where you end up. Got it? Yeah? Okay, so if you started, like, let's go back to example 1. Let's say you started with 120 gallons of water in the tank to begin with. Then to find out how many total gallons of water are in the tank instead of how much has come in, you do 120 plus the integral from 0 to 5 of root t plus 1, right? And then for part B, if you want to know your actual location and you know that you started 57 miles from the starting point, then it's 57 plus how much total displacement you've accumulated from 0 to 3, right? Okay, so you always add the initial condition that they give you to start with. Are you with me?
Yeah.
Yeah? Okay. All right. Now, a lot of times they're going to give you graphs like this where they give you g of x and they ask you to analyze things about that. So what I want you to do is anytime you see this, like g of x equals the integral from 0 to x of f of t dt, then I want you to write probably in part A, like somewhere in like one of the boxes that they give you, that g prime of x equals what? So if I took the derivative of this integral, fundamental theorem of calculus, it's just f of x, right? Do I need to multiply by, well, I'd multiply by 1, right? And then 0, f of 0, the derivative of f of 0 is 0. So we just have f of x. Make sure you make this statement. so that anything you're referencing, you have this statement already here. Okay. If I want to find the area from 0 to 0, if I want to find what g of 0 is, so I integrate from 0 to 0 on this function, then what's that? Yeah. And if I integrate from 0 to 1, then g of 1 is, and if I integrate from, so if I want to find g of 2, I integrate from 0 to 2. So 2, 4, 5. And then g of 3 will be the integral from 0 to 3, 5, 6, 7. And g of 6 will be 7, 6, 5, 4, 3. Are you with me? 3? And g of 7 is subtract 1, 2. Right? Okay. Tell me where is g of x increasing? So this is g prime. This is the graph of g prime.
0 to 3. Yeah.
My g's wrong. From 0 to 3, yeah. How do we know that? Because g prime is greater than 0. Good. Okay, where does g have a maximum value? Yeah, at x equals 3 and y. G prime goes from positive to negative, which means that g is going from increasing to decreasing. But we want to refer to g prime since we have g prime. Okay, sketch a graph of g. Then let's plot these points. 0, 0, 1, 2, 2, 5, 3, 7, 6, 3, 7, dose. And since the derivative exists for all these values, then you know you have a smooth and continuous curve. Okay. See how we have a maximum on the original where the first derivative equals 0. And then we accumulated area up until 3, and then we decreased our area, so our function started decreasing, right? Okay, cool. I want you to do example 4. Only go up to I. Don't do example 5 yet. Let's just do example 4. It says in. Oh, and for example 4, just do split it right here, because I'm going to have you use this table again for example 5. And then evaluate it also at 6, 8, and 10. But just find, put your answers here for this integral. We're going to use the same graph for the second one. So if we're integrating from 0 to 0, then your f of x would be 0, and then go from there. Okay. thing didn't print very well, did it? Did you finish the first part? Yeah. Okay. Does your graph look like that? Yeah. And then your domain would be 0 to 10. Your 0 is at 0, 0. Your total change is the f of 10 minus f of 0, which is 6. And then total change is equal to the net area, because that's a fundamental theorem of calculus. And the maximum value of f is 12. It occurs at x equals 6, and the range is 12. If you did this in interval notation and you said 0 to 12, that's fine. Or like 0, 12, that's fine. But for this purpose, I'm just going to say 12. Okay, now let's go to this, where instead I start at 3 instead of 0. So if this is a 3, then up on this is why I have you divide the table. Then how do I integrate? Because this one I'm going to integrate from 3 to 0. So how do I find the area of 3 to 0? It's what? Negative what? Yeah, negative 4.5. Because you're going backwards, so it's positive area, but since you're going from 3 to 0, it's negative 4.5. Then if I calculate it at 1, then it's what? Just negative 4, right? And if I calculate it at 2, 2.5, negative, right? And if I calculate at 3, what's the integral from 3 to 3? 0. And then the area from 3 to 4. and the area from 3 to 6, and the area from 3 to 8, and the area from 3 to 10. Okay, so if we plot that one, 0, negative 4.5, 1, negative 4, 2, minus 2.5, 3, 0, 4, 3.5, 6, 7.5, 8, 4.5, and 10, 1.5. What does it look like? Same graph shifted down, right? So the question is your interval of increasing and decreasing always the same?
Yeah.
Is your maximum always going to be at the same x value?
Yeah.
Is your concavity always the same? Right? So the first derivative and the second derivative, it doesn't matter whether you start at 0 or whether you start at 3. The only thing that changes is what your starting x-intercept is, right? So instead of your starting x-intercept being at 0, this one would be at 3. So if I wanted to integrate from 4 to x, then all I have to do is make this point at 0, 0, but it's the same shape of the graph, right? If I wanted to start my graph and go integral from 6 to x, then I would have this point would be on the x-axis and it would just be really low like that. Okay. So what is the 0 of g? It's at 3, 0. What is g of 0? Yeah, 0, negative 4.5. The domain is from negative 4.5 to 7.5. No. Oh my God, I'm doing range. 0 to 10 still. I'm like ahead of myself. Total change is still f of 10 minus f of 0, which is still 6, right? The maximum value of g for this one is 7.5. It still occurs at x equals 6. And then the range is still 12. That's why I wrote it as 12 here, so that I could say 12 here. Okay, and then it's to sketch the graph in green, but I did it in red. Okay, so to summarize, the relationship between all f of x equals the integral from k to x of f of t dt as k takes on different values is it's the same graph with a transformation, right? So what point must lie on the graph of any given family member? Because we're assuming that we're starting with k. Yes. K, 0 is your starting point. Right? As k takes on different values, the function integral from k to x of f of t dt graphs as what kind of transformations? Vertical transformations of one another, each containing the particular point k, 0. Even though the lower bound changed, is the derivative the same? Yes. Okay, so your derivative doesn't change. Your intervals of increasing and decreasing doesn't matter where your initial value is. It's the same throughout. Yeah, it's because when you take the derivative, the plus c doesn't matter. Okay, cool. So try example 6 now on your own, and we'll check in a minute. we're going to do particle motion, but just 2 examples of particle motion. And then that's it. Physics, yeah.
Ooh. That's gonna be
So for this one, okay, for this one, this is little f of t, and it says capital F of -3 is -8. So right here, I always like to put this, and I'll just say like f of -3 equals -8. So if I'm finding the area, or sorry, if I'm finding the value of f of 2, I want to do, what you're really finding is you're taking f of -3, and then you're adding what? The integral from -3 to what? 2 of f of t dt. Okay, so f of -3 is -8, and we add 10 plus 26.
makes sense.
And we get 28, right? Right. Okay, try f of 6 and f of -5. Mm-hmm.
Yeah, what's wrong with you?
What I did is I subtracted 10 and 8 from 10 and then added 1.
No, you can just add 10, 26, 48. You got
Oh,
50.
that's only, you take 10, you subtract 8, add the 2 to 14, and add 16 plus 36. Whatever John said. Disagree? Yeah, you're unsophisticated. You're uncultured in maths.
Okay, what did we get? Did we get
34.
34 and -26?
Yes.
Okay, cool. Since the area under f is positive on the interval from -3 to -1, we know the graph of f must be increasing on the interval. And since the area under f accumulates at an increasing rate, we know the graph of f must be concave up. The area under f on -1 to 2 accumulates at an decreasing rate. So f must be concave down on the interval. Cool. So now sketch a graph of f, show extrema, inflection points, and horizontal tangents. So we have at -5, do we figure it out? It's -26. At -3, we're at -8. At -1, we're at 2, right? At 2, we're at 28. 4, we're at 20. And then 6, we're at 34, right? Okay. So, what are we? We're decreasing, so we're concave down up until... How come my -3 is not on here? I put it in the wrong spot, guys. Yeah. Is this okay?
Yeah.
Okay.
You're just like blocking.
So we are concave down, then concave up. And then concave down until 2. How come I didn't plot 2? Oh no.
Not again.
Fart. I thought it was amusing. We're still concave down.
It's okay. Wait, you went from concave down.
Because we're concave down until 3.
Oh,
And then at 3 you switch to concave up.
so it was a nice and
From 3 to... Really, I should go 3 to
we just never do graphing on tests.
Please.
that point.
It's gonna be painful for both of us.
This is fun.
Dude, I gotta get one of Christian's calculators to do all this math.
Okay, that was not too bad, right?
I should basically get a phone to start
Okay, excellent.
How come this battery never dies?
2 particle motion. Oh, still don't.
Physics.
Thanks. We have an inflection point at -3, right? Shh. We have an inflection point at -1. We have an inflection point at 3. And we have an inflection point at 5. Because that's where you reach maximums and minimums on the first derivative. Okay, position, people.
Position. You could have said positions.
Position is S of t or x of t. Now, if they ask you for position and you're given velocity, then you do the integral of velocity to some value here. No. So integral of velocity only gives me total change in position, right?
Yes.
So for position, you have to add in a starting point. So some like S of k.
What?
Well, because I put k on the bottom here. But you can put A if you want. Do C, whatever you want. Sure.
Okay.
Be your own person.
Okay.
Okay. Average velocity is what? No, don't do that. Average velocity we find.
Second line.
Yeah.
Average energy.
This is if you're given position function, right?
Yeah.
Yeah. Okay. Or you can do this. Average velocity, you can find the integral from A to B of velocity over B minus A. This is the same thing. But it depends on whether you're given the velocity equation or not given the velocity equation. Does that make sense to you?
Yeah.
Because if I integrate velocity, what do I get? position at B minus position at A, right? Total change in position. So this is equivalent, this is the same thing as this. It just depends on whether or not your original function was velocity or if your original function was position. John.
You do B to A, integrate from B to A over A minus B.
Yes. Yeah, if you want to switch it, you can switch it. Instantaneous velocity is v of t, which is s prime of t, right? Now, speed is velocity without direction. Acceleration is the derivative of velocity or the second derivative of position. Displacement is total change. So that is just the integral from A to B of v of t dt. Okay, I remember displacement as the integral of velocity. And then distance is you don't care whether or not your area is positive or negative, you're going to add it all the time. So it's the integral from A to B of absolute value of velocity, because we're going to take out direction. I don't care which direction I'm going, I just want to find total whatever accumulated. I remember this as the integral of speed. So displacement, I think, integrate velocity, distance, integrate speed. Put the absolute value signs on the inside of your integral, not on the outside. That's a big mistake. Okay, and then we're not going to do these because physics does these, so we don't need them in this class. Well, you want to know what free fall motion is? Oh, capital G? Negative 9.8 meters per second squared. 32 feet per second.
9.8.
Negative 9.8 for meters per second. And then 32 feet per second. Okay. Let's do example 1 together. Then you're gonna skip and you're gonna do example 5 and example 6. And then we will save 7 and 8 for later. But we won't do 4 or 3 or 2. What? Oh, trig. I just gave you a trig sheet.
I know, I don't like it. At least we're gonna have to use it.
It's not bad. It's so fun.
Yeah, just to remember it.
It's a lot of memorization.
It is. And then it's like everything kind of tips you out, and then you're like, oh,
Yeah.
I wasn't.
Okay, ready? What was that, Marco? I liked it.
Wait, can we do particle motion with vectors? That's the most fun.
No. We'll do vectors in units 7 or 8. Okay. So if you want a position function for the particle, if they don't tell you to solve for anything, then all you have to do is write s of t equals, and then let's do the accumulation function. Now, notice it says the position of the particle at time t equals 1 is 3, right? So I can say my position is going to be 3 plus my total change of velocity
Can you show V of t?
yes, you can just write v of t. From what to what? Yeah, let's go 1 and then x or t, whichever one. Then this would be s of x. Okay? Find the displacement of the particle from 0 to 6. So that's what? Just the integral from 0 to 6 of velocity. Okay, I gotta integrate this. T cubed minus 5t squared plus 3t from 0 to 6. Don't need the plus c because we've got a definite integral here. And so this will just equal 6 cubed minus 5 times 6 squared plus 3 times 6. And 0 plugged in is 0, so we don't have to worry about it. Because for definite integrals, the plus c will cancel when you plug in 6 and then you plug in 0. Like if c was 2, then it would be like plus 2, and then 0 plugged in would be minus 2, and they would cancel each other out. Okay, now here's the problem, and distance is the integral from 0 to 6 of the absolute value of velocity or speed. Integral of speed, but we've got an issue here. Yeah, you do. Velocity, right here. So if I factor velocity, then it's gotta be 3 and 1. Minus 1, minus 3. Okay, so my velocity number line, 1/3 and 3 goes positive, negative, positive. Right? Okay, so here's the problem. I've got this negative velocity, but I've got to make it positive to integrate it, right? Yes? Now, if you have a calculator, very easy. Just go integral 0 to 6, absolute value, and then plug in this velocity, and it does it all for you. But if you don't have a calculator and you have to do it by hand, then you have to separate it into 3 parts. You have to go integral 0 to 1/3 of velocity, and then the integral from 1/3 to 3 of velocity. But I need to make this positive, and it's going to come out negative. So I'm just going to do a minus. So what I remember is if it's positive, keep it positive. If it's negative, make it negative. And if it's positive, keep it positive. Yeah. Yes. So you could keep this as plus, and you can flip these two if you want to. Or you can keep it as plus and put a big absolute value sign on the outside of it, whichever one you want to. And then we have to do this for all 3 parts here. But we're not going to do it.
I can see this on
Huh?
Delta Math taking out.
Yeah, it really does.
Delta Math's gonna be like,
You can see
in
Delta
form,
Math.
right
I
the
can see
answer,
Delta
and then you
Math.
write the answer, it's like not simplified enough.
Yeah.
Chem Club.
Okay, So all I want you to do is finish 5 and 6. And once you finish 5 and 6, then you can come pick up your quiz from me. But finish 5 and 6 first. And I will put the answers up for you.
Do we have to use feet per second?
Yeah, use feet per second because it's just easier. Because all of the prompts are in seconds. So if you don't use feet per second, then you're gonna have to, yeah.
Oh, I was probably digging some graves. Why is it dusty?
How far is distance? But you can use your calculator to calculate it.
Wait, how do you get dust out?
Maybe use a piece of tape. And then it, like, the dust will come off on the tape. I have tape on my desk if you want a little bit. Yeah.
Do you use acceleration or do you use velocity?
For B, for A, you integrate acceleration to get velocity, but don't forget to add 66. Yeah.
Okay.
And then for B, you integrate your velocity to get your distance. Yeah. Absolute value.
I don't know, man. I'm sorry.
Absolute value doesn't matter.
No, it's always positive. Yeah.
If you look directly into it, you can see it.
John, finish 5 and 6. They won't take very long. And then you have time to work on your quiz corrections and stuff.
Okay.
Okay.
How fast are you going? Going back a second.
Every single day, all year in math class, Jody turned around and tried all her work on my desk.